Hello guys, welcome back to my channel Gamma Die Gamma. And in this video I would like to do an interesting question. The result, if you might have already guessed by looking at the title of the video. But in any case, the result isn't that surprising. It's actually pretty trivial on first sight, but this question was really interesting. So let's get started. Okay, so here's the problem. I've denoted it in I, as always. Integral from 0 to infinity sine of pi x times sine of 5x divided by 4 minus x squared dx. Well, for this I'm going to use a complex analysis. So I need to define sort of a general function f of z to be sine of pi z. And instead of sine of 5x, I can write e to the I. Instead of the arbitrary number 5, let's have alpha z divided by 4 minus z squared. Okay, and since this is complex analysis, I'm going to need a contour. And now contour check. Now in selecting a contour, I just notice this jump over here at, well, x equals -2, and again this jump at x equals 2. That's because those points are definitely poles of f of z, but the thing is that they're lying on the contour, so we either include them or exclude them. So it's better to exclude them, otherwise you're gonna have little problems. Well, this is the real axis, this is the imaginary axis. Call this negative r, call this positive r. This is the 0, path gamma. Okay, so the contour integral f of z dz equal to, well, the contour integral on the negative part, negative r to 0 f of z dz, plus integral on this positive part from 0 to r f of z dz, plus integral over gamma f of z dz. But the catch here is we also have to include these integrals over paths, I don't know, what do we call this, beta 1 and beta 2. So integral over beta 1, integral over beta 2. Fair enough. Notice that, at least on this negative patch, z is equal to -x. So when we do that, we simply end up with integral from r to 0 sine of pi and -x will give you a negative e to the negative I alpha x over 4 minus x squared, and we have a negative because of the dz, which will make this a plus. And on this patch, z is equal to x, so nothing changes. And the beta 1 and beta 2 parts I'll do on a fresh page, and also the gamma on another fresh page, because we'll have to use Jordan's lemma to make this go to 0. Okay, so I didn't write the other terms, but you get the hang of them. There's beta 1 term, the beta 2 term, and the gamma term in the contour integral f of z dz. Okay, see you on a fresh page. Okay, so for this guy basically, we have x equals -2, x equals positive. That these are the points we excluded, and this is beta 1, this is beta 2. So for beta 1 now, we need to parameterize z as -2 plus epsilon times e to the I theta. Well, you can call the radius of this guy epsilon, so this will be, well, negative epsilon and epsilon, for example. Just like this, how this was r and negative r. It's like a smaller semicircle here. Same thing here. Small epsilon epsilon. So first let's do this negative, x equals -2. So that's how we'll parameterize in this case. And theta is going from 0 to pi, actually pi to 0. If you want to talk about anti-clockwise convention, the integral will go from pi to 0 because of the convention. dz is going to be epsilon I e to the I theta d theta. And we substitute this parameterization in f of z. So we have e to the I alpha -2 plus epsilon e to the I theta divided by we have 4 minus z squared, and when we do all that calculation, we have 8 epsilon e to the I theta. Well, I think it's going to be 4, 2 times 2, yeah, 4, not 8, minus epsilon squared e to the 2I theta, and then we have like the sine part. So sine of -2 pi plus pi epsilon e to the I theta, and we have the epsilon I d theta. That's for at least for beta 1. And when I can simplify stuff, the sine of -2 pi plus pi epsilon e to the I theta is just going to be, well, I can separate this out first. -2I alpha e to the I alpha epsilon e to the I theta over, well, I can divide by epsilon actually in the denominator. So 4 e to the I theta minus epsilon e to the 2I theta. Well, I forgot an e to the I theta actually over here because of the dz. So I can just like write it here maybe. Sine can be reduced using basically the fact that 2 pi acts as 0 in the periodicity of the sine. So pi epsilon e to the I theta d theta, that's beta 1 actually. I can divide by epsilon. Sorry, I did divide by epsilon, so I can divide by e to the I theta again. -2I alpha e to the I alpha epsilon e to the I theta over 4 minus epsilon e to the I theta sine of pi epsilon e to the I theta d theta. And now I would like to take the limit as epsilon goes to 0 because I want to make this path as this looping over the poles as inconspicuous as possible. and because of the convergence of the integral, I can take the limit inside. When I do that, all of this, the exponentials will become 1, denominator will become a 4, but there's a sign which will make everything go to 0. Now for beta 2, we essentially do the same, except that now the parameterization 2 plus epsilon e to the I theta is going to work, and again theta is going to range from 0 to pi, and our integral, although will go from pi to 0 because of the positive anti-clockwise rotation convention, if e to the I alpha 2 plus epsilon e to the I theta sine of 2 pi plus pi epsilon e to the I theta epsilon I e to the I theta d theta over negative 4 epsilon e to the I theta minus epsilon squared e to the 2 I theta. You can cancel epsilon and e to the I thetas everywhere in the numerator and denominator. We have e to the 2I alpha e to the I epsilon alpha e to the I theta sine of pi epsilon e to the I theta. We still have an I though, divided by negative 4 minus epsilon e to the I theta d theta. Now take the limit as epsilon goes to 0, just like beta 1. Because of the sign, we end up with 1. So both of these loopy guys go to 0. That's really nice because now we don't have any random mess in the original contour equation. Now we did the beta 1 and beta 2s. Let's look at this semicircular path gamma in a procedure that's relatively well known to us compared to the beta integrals. Jordan's lemma on a fresh page. See you there. Okay, so we start off with the basic sets of inequalities that we've always known. Now we can substitute for f of z. So integral over gamma of e to the I alpha z sine pi z 4 minus z squared mod of that mod of dz. Now for the semicircular path, z can be parameterized r e to the I theta. I'm not adding anything like 2 or something because we're centered at the origin. Back then we were centered at negative and positive 2 respectively for the beta integrals. And theta is going from 0 to pi again. But here we can directly go from 0 to pi e to the I alpha r e to the I theta sine of pi r e to the I theta over 4 minus r squared e to the 2I theta. dz is going to be ri e to the I theta d theta. Okay, we can use a basic bout of inequalities. Sign is trapped between negative 1 and positive 1, so mod of a sign will be 1, so this guy will go to 1. This will just become I and e to the I theta will go to 1 again in the mod. I can write this as e to the I alpha r cosine theta plus I sine theta. We have an r. D theta. Now we have well, in the numerator we have e to the I alpha r cosine theta multiplied with e to the negative, because I and I will make a negative 1, alpha r sine theta r d theta, and in the denominator we can use the reverse triangle inequality again, 4 minus r squared, because modulus of e to the 2i theta will be 1. The modulus of this guy will be 1 because e raised to I times anything is 1 in modulus. And for this other guy, we can use a Jordan's inequality. We get e to the negative 2 alpha r theta over pi divided by 4 minus mod r squared mod r d theta. And now we can use Jordan's lemma, at least the statement of Jordan's lemma. Okay, I could have basically just reduced it down to one maximum of this function apart from the exponential and then just directly use Jordan's lemma, but I just like to show the steps for you to understand using Jordan's lemma, and you can watch the video on that if you don't understand what I did. I have this less than pi over alpha, and I have modulus of r is going to be r and 4 minus r squared. Now I'm free to take the limit as r goes to infinity. Doing so, I have 0. Which means this goes to 0. Because the mod can't be negative, the only way for this series of inequalities to be true is for this guy to be 0. So that gets rid of the integral over gamma. Now let's conclude something. Okay, so this is the loop equation we had, the contour equation. This went to 0, so did this, so did this. And this is actually equal to, we can use residue theorem or Cauchy-Ghursa now in this case because there are no residues. Because no poles inside the contour, we skipped over the poles. Remember, the poles were 2 and negative 2 and we just skipped over them, right? That's how we got the beta 1 and beta 2 integrals. And there's no poles of f of z inside this contour anyhow. So we have to use Cauchy-Ghursa, no poles, no residues. So the loop equation has to equal 0. And now what we can do is we can take the limit as r goes to infinity. We can multiply a negative, flip the order of integration from r to 0 to 0 to r, which means contour integral f of z dz is equal to integral from 0 to r, limit as r goes to infinity. We can club both of them under a negative. So e to the I alpha x sine of pi x 4 minus x squared minus e to the I alpha x sine of pi x over 4 minus x squared dx. And it gives 0 by Cauchy-Ghursa, which implies that integral from 0 to infinity of sine of pi x over 4 minus x squared e to the I alpha x minus e to the, I think there should be a negative alpha, at least over here. Yeah, because that was the negative parameterization. Negative I alpha x dx. We can multiply and divide by 2. Because now notice this guy is just sine of alpha x. So we have sine of pi x, sine of alpha x divided by 4 minus x squared is 0, which means, and this guy, leave the 2, we can forget the 2 because there's a 0 here. This guy precisely is I. I is 0. Well, I was when alpha is 5, we can just make that, we can just show that for any arbitrary alpha this is 0. So obviously for alpha equals 5 this holds. I hope you enjoyed this video, guys. Please like, share and subscribe to my channel. Recommend me to your friends. Spread the word of Gamma Digamma in the math community. And in the meantime, stay home, stay safe, keep doing math and peace out.